What did we discuss last time? What did we talk about? Right. Talked about gram. What is this? It's a procedure. What is it? Right. If you have a set of vectors S, I'll call it U. U1, U2, U3, and Ui belongs to Rn. Then, and if this is not orthonormal, this is just some basis. A linearly independent set, not an orthonormal basis for its span. How do you convert it into an orthonormal basis? You do the Gram-Schmidt procedure. And how do you do that? What is the procedure in general? If you have if you have p vectors, what is the first thing you do in the Gram-Schmidt procedure? A. Okay, how do you get Q1? Right, you take the first vector, normalize it. Okay, and then how do you get Q2? No, describe it in words. Let's forget about the exact algebra. What do you do to get the next vector? You project the second vector onto the span of Q1, find the error between U2 and the projection, that will be orthogonal to U1, and you get Q2. Then how do you get Q3? Right, you take U3, project it onto the span of Q1, Q2, and you continue. And then this will give you a set of vectors Q1, Q2, Q3, and this is guaranteed to be an orthonormal basis for the span of set of vectors U. Okay, and then what did we talk about? Yep. Right, what are orthogonal matrices? If a matrix Q is an orthogonal matrix, first of all it's a square matrix, and Q inverse is Q transpose. And what can we say about the columns of Q? Are the normal. In fact, the columns of Q form an orthonormal basis for Rn. Yeah. Okay. Then, what did we talk about? Yeah. Matrix inverses. No. We talked about another important topic. What is this? What is the QR decomposition? You'll have to be louder. What is it? Q into R. But what are the conditions on A? Yeah, it's got full column rank. That means it has to be tall or square. It cannot be fat. Okay, if that is the case, let's say this is n cross m, where n is greater than m or equal to. Then what can we say about these two? What is the shape of Q? N cross m. And this one? Then what can we say about R? Yeah, this is a triangle. And how is this related to Gram-Schmidt? Yeah, so if you do the Gram-Schmidt procedure, the columns of Q will be the orthonormal basis that you generate using the Gram-Schmidt procedure. Okay, and R matrix simply tells you how to recover your original vectors by using the new orthonormal basis. Okay, and then yeah, we talked about matrix. Okay, we didn't specifically talk about matrix inversions, but we started talking about. This was the module, and then we started talking about something else. Okay. Now, if you imagine this is R2, and we take this as the origin, if I draw a vector A, right? Okay. So now we're dealing with R2, and we've assumed this to be the origin. Now, this point here, is with respect to the origin, is represented by this A vector. Right? The question is, if I ask you what are the numbers corresponding to A, what would you tell me? Is it 1, 1, minus 3, 4, 103, root 2? What is it? Well, it turns out if you want to assign numbers, then you have to have a reference or a basis. Okay. Like for example, as we discussed last class, if you have a body, if you want to measure its mass, you have to have a reference with respect to which you measure its mass to assign a number to that to the quantity which tells you about the mass of the object. Similarly, if you're talking about a vector quantity which has both some magnitude and direction, and if you're interested in assigning numbers to this, we are interested in representing this vector in terms of numbers, then you have to have some reference, and that reference is what is called as the basis, which we've talked about before. And to do that, all you have to do is you arbitrarily choose a reference for yourself. For example, I could say I choose these two vectors as my references. Okay, I'll call it E1 and E2. Now, because E1 and E2 form a basis for R2, and this I have chosen arbitrarily. I can choose any E1 and E2 as long as the vectors that I've chosen form a basis for the space that you're dealing with. Then it turns out you can use that as your reference to assign numbers to the vectors that you're interested in for this space. So if I choose E1 and E2, okay, I can assign numbers to A because E1 and E2 form a basis for my original vector space from which A comes. So A comes from this R2. These two form a basis for the span of these two vectors is R2, and this is a linearly independent set. Okay, that means this implies that if I have a basis, if this is the basis, then I can represent every vector in this space as a linear combination, as a unique linear combination of my basis vectors. That means I can write A as some alpha 1 E1 plus alpha 2 E2. Okay, if I can do this, right? If all of us have agreed that we will use E1 and E2 as our basis vectors, then to communicate information about any vector here, all I would need to give you or you would need to give me are just these two numbers, alpha 1 and alpha 2. Okay, that means the representation of A, a numerical representation of A, in terms of this E1, E2 basis is simply alpha 1, alpha 2. Okay, if we always agree this is what we're going to work with, then I don't have to tell you this because this we've agreed upon. All I have to tell you is this, right? But then the issue is there are infinite number of basis vectors that you could, or bases that you could have chosen for this vector space. For example, I could have chosen this, not E1 and E2, but maybe this one. This one, I'll call it U1, U2. Now, I cannot, alpha 1 and alpha 2 will not work here because, first of all, because we know that if we are dealing with the basis, alpha 1 and alpha 2 are unique to the basis E1, E2. Okay, So if you try doing this alpha 1 u1 plus alpha 2 u2, this will not be equal to A. Okay, that means, but because u1 and u2 form a basis for R2, there are definitely some other numbers beta 1 and beta 2 that will give me A. Means the same number or the same vector in the u1 u2 basis as a different representation. Okay. And see, so far when we before we started putting numbers to these, we were simply dealing with these geometric quantities, some flat space, some plane. We chose an origin and we said we are interested in this point. Okay, and this vector, this arrow represents that point. Then I said, oh, let's choose two other arrows so that they are not collinear to each other. If we choose this as some reference that all of us agree on, then I said you can represent this vector A in terms of E1 and E2, right? And I said you can do that by a linear combination like this. Even though I've written it algebraically, what we are talking about here is a geometric operation. The geometric operation is you take E1, you scale it by alpha 1, whatever that number is. You take E2, you scale it by alpha 2, and then if you add those two vectors, then you will get to this point. Okay, that's what the statement means. Even though I've written it algebraically, this is a geometric statement. Okay, because alpha 1 and alpha 2 are numbers that tell you how much to stretch each of your basis vectors. These numbers are, if we agree on the same base, agree to work with the same basis, then we only need these two numbers. That's how these geometric quantities get converted into numbers, because we've chosen some other geometric quantities as our reference. Okay, the same applies here. Beta 1 and beta 2 simply tell you take these two reference vectors, scale them by beta 1 and beta 2, and if you add them together, you will get A. Okay, that's how the numbers relate to some geometrical quantity that we are dealing with. Okay, now the question is, see, of course there are different bases. People like to work with different bases because some bases have nice properties, some might not, right? So if we have different bases that people work with, then we would like to know if and how we would go back and forth between different bases. Okay, and that is where the idea of the matrix inverses turns out to be very useful. Okay, now let me ask you this question. Let's go back to this picture, right? This is some vector B, some vector A1, some vector A2. Let's say I've chosen A1 and A2 to be my basis for this space. So my basis is this set A1. Okay. So now I ask you, can you find the representation of B in terms of A1 and A2? How would you do that? Geometrically? I'm asking you what those numbers will be. How will you find out those numbers geometrically? Sorry? What? How would you do that? Yes, not x and y. No, there is no x and y component, right? What is x and y component? I don't know what x and y is, because for me my reference is only A1 and A2. How do you find the components of B along A1 and A2? How do you do the projection? Okay. See, if you say you want to represent A1 and A2 in terms of, you want to represent B in terms of A1 and A2, you're talking about something like this, taking the linear combination of A1 and A2. whenever you add two vectors, you do a parallelogram addition of vectors, right? That means you take A1, you scale it by some amount, you take A2 and scale it by some amount, and if you add them together, that point should come here. That means this B vector is essentially the diagonal of some parallelogram. Yeah, and that parallelogram has to be like this. N parallel to this. Is it clear? That means I have to take A, stretch it by so much. I have to take A1, stretch it by so much. Take A2, stretch this by so much. And let's say that is some comma 1, comma 2. That gives me this and this. If I add these two, I get this. So you're right in saying you have to find the component of B along A1 and A2. It's just that in the previous module, we looked at components, and to find the component along a vector, we always drop the perpendicular, right? And then we said this vector is the component of this vector along this. It's true only if you're talking about, or let me put it this way. There we were always dealing with vectors that were orthogonal to each other. When you are trying to represent any vector B in terms of an orthonormal basis, then you always drop perpendiculars. But if you're dealing with a non-orthogonal basis, orthonormal basis, then it turns out that the correct way to find the components is not by dropping perpendiculars, but you drop lines parallel to all the other vectors in your basis. For example, here, the line I dropped from B to A1 was not a line that was orthogonal to A1, but a line that was parallel to A2. Similarly, the line I dropped from B to A2 is a line that is parallel to A1. Okay, so often what you will find is this idea of dropping perpendiculars is true only for orthonormal basis. If you're not dealing with an orthonormal basis, then you don't drop perpendiculars anymore. Okay, so when you talk about when you have an non-orthonormal basis, we find the components along the different basis vectors, and these components are components. For example, the alpha A1 is the component of B along A1, but projected along A2. That means the line that you drop has to be parallel to A2, and so on and so forth. Okay, geometrically this is how you find out. Okay, now if you go back and now talk about the last three modules that we've discussed, I always wrote down vectors in terms of numbers, right? I always wrote like this. I said 1, 3, minus 1. Okay. Now we should go and question what was this represented in, right? Because this number does not make sense unless and until you know what basis this corresponds to. Okay. Often, when you see somebody write something like this, or if I in class if I say something like this, you always assume that if the basis is not mentioned, reference, then you always assume that this is in this what is called the standard basis. Okay, a standard basis is essentially an orthonormal basis, and the basis vectors are essentially these EI, unit vectors. What are unit vectors from our first class? Let's say this is from Rn. What is the definition of that? Right, everything is 0 except the ith element is 1. Okay, so whenever you see something like this and the basis is not mentioned, you assume it's in the standard basis, and the standard basis is essentially your n unit vectors. Okay, now in space, what directions those take, that does not matter. All you need to know is if the basis is not mentioned, then we assume it's in the standard basis. So far, everything that we talked about, where I did not explicitly say what basis we were working with, the assumption is everything that we dealt with was in the standard basis, and because we were working only in one basis, we didn't have to bother about conveying what basis we were working in. Like I said earlier, if we always agree to work with E1 and E2, then I don't have to tell you this every time. We can just agree to just talk about this, and we assume that all of us know what we are talking about. Okay, all right. Now, so that's clarified. If you see numbers like this, nothing's mentioned, it's in the standard basis. Now, let's go back to this problem. And let's say we represent A1 in the standard basis. I assign some numbers. Okay. Okay. And A2. A1 and A2 are some vectors represented in the basis, in the standard basis. Okay. Now, let's say B has some representation as well in the standard basis. Okay. Now, what I'm interested in is, because I said we want to be able to go back and forth between bases, I ask you, what is the corresponding representation of B in this basis? That means I want exact numbers for gamma 1 and gamma 2. How would we find that out? Not geometrically, now we have to deal with this numerically. Right, so what we are essentially saying, well, if you want to represent B in terms of A1 and A2, then I take gamma 1 times 1 minus 3 plus 2 times 2, 3. Okay. For now, maybe I'll assume I won't use gamma. I will use x1 and x2, and that will become clear why I've chosen this. And this should give me 1, 1. Now, how do we find x1 and x2? Well, yeah, exactly. We can write this in a matrix form, no? What is it? So, yeah, x1, x2. Now, how do we solve for x1, x2? Yeah, this is Ax equals B. Yeah, exactly. I can find x because A is, well, is A invertible? Well, we can write it like this, but only if A is invertible. How do we know A is invertible? A is not single. It's a square matrix, okay, and then, but it's not enough. Why is it full rank? Yes, because the columns form a basis for Rn. That means there are n linearly independent set of vectors here. That means this is invertible. That means I can do this. Then what does A inverse mean? What does A inverse give me? Wait. Exactly. That means A inverse has the meaning now. Right? A inverse is just not some abstract quantity. A inverse is that matrix which will give you what? Or it will give you the representation of B in what? Which basis? What is BB basis? Yeah, exactly. So A inverse simply gives you the representation of the vector B in the basis formed by the columns of A. Yeah, and that is, see, in fact, that is why you can write it like this. Because here, when you say AX, when you post multiply a matrix by a column, what are you doing? If you post multiply a matrix by a column vector, what operation are you doing on the columns of the matrix? Yeah, you're taking the linear combination of columns of A, right? And when you say you're representing, you want to represent B in terms of A1 and A2, you're doing AX equals B. Okay? And X is the representation of B in the columns of A. Okay? And A inverse gives you that. So now when you see A inverse, one way to think about A inverse is whenever you see this appear somewhere, one possible interpretation could be you are simply changing basis of B from the standard basis to which basis? Basis formed by the columns of A. That's one interpretation of A inverse. A inverse is, let me write it down. So A inverse is a matrix that allows us to find what? Or allows us to change basis. Okay. Let me ask you this. Does A allow, can you think of A as a matrix that allows change in, wait, let me restate it. Is A a matrix that allows you to change basis? If so, to what basis does it allow you to change to? You understand the question? You started with A, the columns of A formed the basis for Rn, and the numbers that you had for the columns of A were all in standard basis. B was in the standard basis. And then we said if you do A inverse B, you get the representation of B in the columns of A. Now I'm asking you, that means A inverse allows me to change basis. I'm asking you, does A allow me to change basis? But see, A inverse and A inverse is just another representation for some matrix, right? Because A is the inverse of A inverse. In that view, does A allow me to, is A also a matrix that allows me to change basis? Yes, if so, what basis do I change to? If I do, let's say I get another vector, C. Okay. It allows me to change to the standard basis, is it? No. Okay, why do you say it allows me to change into the standard basis? Yeah, that's correct. What is X? X is the representation of B in the A1 A2 basis. This allows me to change basis to the standard basis. This allows me to find the representation of B in the standard basis. Yeah. Okay. All right. So with that, and here, if A was orthonormal or orthogonal, okay, then the change of basis is simply A transpose. Yeah? The change is easy. That's because if you remember how you represent a vector in terms of an orthonormal basis, you get the components by simply doing Qi transpose X or P. Okay, the components are easy to find. Okay, so that's the interpretation of A inverse. Now, the matrix inverses, right, require that A be square and full rank. Okay. And we know A inverse A inverse A, it's In. Okay. Now what? Okay. I mean, this we took as definition. I simply said this is how it is, and then we agreed it's okay. It turns out that is true. What if A was rectangular? Okay. If A was rectangular, the question is now, can you have an inverse? That's one type of inverse. Okay. When A is rectangular, the question now is, okay, if A square and full rank, then there is this one unique matrix that whether you post multiply or pre multiply, you will always get the identity matrix. If A is rectangular, the question is there a matrix such that B times A gives me I, and A times B gives me I. No? Is this even allowed? If it's rectangular, this is P cross Q. Let's say this is Q cross P. Then what will I get? I get Q, IQ. Okay? Because I has to be square. I cannot choose anything for anything here. It has to be Q. And this has to be P because this is P. Okay. The question is that possible? Let's take the example of a tall man. Yeah. That's what we'll talk about. Is it possible? Okay. Let's say you have a tall matrix. Okay. P is greater than Q. Now that means we need to find the matrix like this. That will give me I. This is identity. And you take the same matrix and you multiply it here, and you get a bigger. No, this will be small. Same size as that. That's this. That's this. Let's talk about this. Okay, it's full rank, right? That means the rank of the matrix is Q. Okay, that means what is the dimension of the column space of this matrix A? This is A. Yeah, what is the dimension of the column space of A? Q, right? It's a size, number of elements in the basis. That means if I do A into B, whatever I produce by this operation has to be Q dimensional. Whatever comes out has to come out of a Q dimensional subspace. It cannot come from anything bigger. I mean, it can be smaller. In fact, it cannot be smaller as well. But depends on what B's are. If I can choose any B here, what I can get out here can at the most come from this Q dimensional basis, right? That means now our goal here is to use this to produce I. Okay, that means we want to produce 1, 1, 1 and zeros here. What is the dimension of the column space of this IP? No. Forget about this. If I have the matrix IP, what is the dimension of the column space of this matrix? This is a P cross T matrix, right? The dimension of the column space of this is P. That means that I can get everything from RP, right? Q is less than P. That means if I have A, everything I can produce comes from a Q dimensional subspace of RP. I cannot produce anything outside. That means it's impossible for me to produce something with A, for me to produce something outside of this Q dimensional subspace. That means I cannot produce IP. Okay, At the most, what I can produce is maybe I can produce q unit vectors from here. That's it. The rest, p minus q unit vectors, I cannot produce because those fall in my left null space. That's a subspace I cannot touch with my A because I don't have enough columns in A. Okay, so if you have a tall A, this is definitely ruled out. You cannot get IP. That means this is not possible. It turns out this is possible. I will let you think about the argument, but here the arguments would be you have to produce IQ. Okay, that means you have to be able to produce any element from this q dimensional vector space. A is full rank. If B is full rank, then you have enough columns here. There are q columns here and p columns here from RQ. If B is full rank, then you can produce anything from RQ from here. That means this is still possible as long as B is also full rank, if A is full rank. Okay. So the conclusion is, if you have a rectangular matrix, you cannot have both of them be true at the same time. Only one of them is true. If it's a tall matrix, okay, it does not mean you cannot find a matrix B that you can post multiply to get identity. What you can do is get a matrix which you can pre-multiply to get an identity matrix. Again, all this applies only if A is full rank. Okay. So for a tall matrix, if it's tall, this is true. This is not true. If A is full rank, you can definitely find B that satisfies this, but you cannot get this. If it's a fat matrix, then you can get this, but you cannot get this. The same argument applies. You can try that for a fat matrix as well. Okay, that means if you have a rectangular matrix, you can either have left inverses or right inverses, not both. If A is square and full rank, you have both a left and right inverse, and in fact the left and the right inverse are the same matrix, which is unique, and it's a single matrix A inverse. Yeah. Right. So now the question is, okay, how do we go about finding it? And before that, if you have a square matrix and it's full rank, the inverse is unique and it can go on either side. If it's rectangular but full rank, I said you can only have inverse on one side, and it also turns out that the inverse is not unique. If you have a tall matrix, there are an infinite number of left inverses that will give you this. If you have a fat matrix, there are an infinite number of right inverses that will give you IP. To see this, let's look at an example. Let's talk about left inverses first. Well, the simplest possible tall matrix is, maybe we do this. Well, is simply a column vector, right? Okay, one column. That belongs to Rn. No, I should not write it like this. It's like this, and A belongs to Rn. Now the question is, how do we this is full rank, A is not 0, so this is full rank. That means it has a left inverse. The question is to find this matrix. Let's call it C. Okay, such that AC equals, what will I get on this side? I, what will be the size of I? 1. Yeah, it will be a 1 cross 1 matrix. That means it simply has to produce 1. How do we find this? Okay, well, let's do a specific example. Can you tell me a left inverse that will satisfy this? Yeah? Can you give me a C such that CA equals 1? 0, 1, yes. Is there another C that will produce that? 1, 0, and half, and there are infinite number of them. Okay. In fact, we can generalize this. If I have a matrix A with one column, okay, if I simply take this, okay, as my C, right? I take the transpose of A and then I normalize it. Okay, in fact, I do this, not just the length, but I normalize it by this number. Okay, what will you get when you do CA? Well, I can take the scalar out. This is A transpose A. This will simply be A transpose A divided by, this is 2 non-square. So this will always give me 1. Okay, so if I choose a C like this, I get 1. But here, this case, that means if you do look at the R2 case, right? And okay, another point. I usually draw stuff like this, right? And then I draw the vector like this. Okay. And earlier, we never talked about what basis we are dealing with. When I draw stuff like this, what basis am I talking about? The standard basis. This is E1, this is E2, that's assumed. Okay. Now this is my vector 1, 1, or my matrix, right, is represented by this vector. Right? Now you have this vector, right? Now, if I take C and simply add, I'll call it some vector B such that P transpose A is 0. Okay, some vector. Okay. Does this also form a left inverse for my matrix A? Basically, I take this and I add this vector B that satisfies this. Well, if I multiply this by A, these two will multiply to give me 1, these two will multiply to give me 0. That means if I choose any vector that is orthogonal to my column of A, then those are all the other possible left inverses that I can produce. Okay, so that's where the infinite number of left inverses come from, because if A is tall, that means the span of A is not all possible vectors in your original vector space. There is still some space left in your original vector space. Those vectors, and from that space you can choose orthogonal vectors and place them here, and that will produce you all the infinitely possible left inverses. Yeah? So that's the idea. So we can generalize this now, instead of talking about something from just one column. If you have A, it's P cross Q, and Q is less than P. Okay. C plus some C cap is a left inverse of A. It will give me I Q. Okay, and the rows of C cap or C cap come from, I'm just going to state this, you can think about why that is true. Left null space. Okay. I'm going to state it without discussing why that is true. I'll leave it as an exercise for you to think about why that is true. If you choose any vectors, you choose a matrix C cap, so that the rows come from the left null space of A, then, and if you add it to some C that is the left inverse of A, then you can produce additional left inverses for A. Okay. Now this brings us to this question. What if I have a system of equation like this, and A is tall, P cross Q, Q is less than P, and rank of A equals Q. Now the question is, okay, we know that this has a left inverse. Is the left inverse useful in solving this equation? Can we solve this equation? Can we always solve this equation? Let me put it that way. Can you always find an x that will give me x equals such that if I post multiply A by x, I get B, when A is tall and full rank? When can I solve it? Not the basis. Yes. So you can solve this if B belongs to the span of A. Okay. We know we can solve it in that case. In that case, we know there is a x that will give me this. In fact, there is a unique x that gives me this. Okay. It turns out that the left inverses will help you find x. In that case, whenever B lies in the span of A. If B lies in the span of A, it doesn't matter what left inverse you choose. Okay, you can choose any left inverse and we multiply it by B. The x that you get, so if you multiply it by B, you get some vector. Okay, and you do this, and you'll get B. Again, this is true only if B lies in the span of A. Okay, otherwise you would see something. Okay, again, maybe this is confusing at this point, but I will make this point anyway, right? If you look at this, right, I've written A times C. I said C is a left inverse for A. Now I've written A times C into B is B. That means AC into B is B. What does it tell me about AC? That's strange, no? Right, but I said C is a left in. I said A is a tall matrix. It only has left inverses. But now I've written A post multiplied by C also turns out it gives me I. No, that's strange, no? Okay, it turns out this is not a problem because this is true only when B belongs to the span of A. If B is not in the span of A, if you do ACB, this is not equal to B. Okay. We've seen something like this before when we were talking about orthogonal projection. If B lies in the subspace onto which you are trying to project, then you get B back, right? It does not mean P is identity matrix. This is true only when B lies in the column space of P. If it does not lie, then you don't get B, but you get P cap, the orthogonal projection of B onto the subspace spanned by the columns of P. It's the same idea here. Okay, AC into B is equal to B only when B lies in the span of A. Otherwise, this all bets are off. This is not true. So, in general, if B does not belong to the span of, well, I should not have written span of A, but column space, just to be consistent, does not belong, then ACB is not equal to B. Okay, what you get is some other vector, B cap. Okay? So this will be equal to some B cap. But the interesting bit is there are infinitely many C matrices. If B lies in the span of A, it doesn't matter what left inverse you choose. If you multiply C by B, you solve this equation. Okay. That's all I wanted to say about left inverses. Now we'll talk about the other right inverses. And right inverses are exist for fat matrices. Fat matrices. If A is P cross Q, P is less than Q, and rank of A is P. Again, we are only talking about matrices that are full rank. If this is the case, then there exists matrix B that gives me I P or IQ. Yes. P is less than Q. The same set of arguments apply now. Okay. There are infinitely many right inverses. Now, if there is, let's say B is a right inverse for A, I can always add a matrix B cap, okay, such that is equal to IP. That means A times B cap is 0. That means A times the individual columns of B cap gives me 0. What does that tell me about the columns of B cap? Where do they come? There are 4 fundamental subspaces, right, associated with the matrix. If the columns of B cap, when post multiplied by A, give me 0, where do the columns come from? Yeah, so the columns of, so here the rows of C cap came from the left null space. So here the columns of B cap the null space of A. We come back to this. The same thing applies. Is this solvable? Can you solve this if this is true? We have a fat matrix that is full rank. Firstly, is it solvable? Is it unique? If it's solvable, is it unique or infinitely many solutions? Yeah? Yes. See, there are more x's than there are equations. That means it's got. Okay, and here it's very, now if there are infinitely many solutions, you could ask, how do I generate those infinitely many solutions? It's very simple. You take B, you take any right inverse B, this is a solution. Because there are infinitely many right inverses, you can enumerate all, you can generate all the possible solutions. If you have all the right inverses for B, then you can generate all possible solutions for x equals B using this. Okay. In fact, if you take AB, okay, you get some x, right? And I multiply it by A, I get B. Is AB equals I now? In this case? It is, because it's a right inverse. This is always I. So it doesn't matter what B you have. AB equals I for any, it doesn't matter what B you have. That means this is always true. Whereas in the left inverse, you had to have that special condition where B belongs to the column space of A. Okay? Now, maybe you're asking, okay, what do these infinitely many left inverses and right inverses correspond to? Okay? Turns out that the left inverses are, okay, when you say you want to solve this, right, you're asking, I have this subspace spanned by the columns of A. You're saying I have a B that might or might not belong to this subspace, the column space of A. You're asking what is the X that gives me B. That means X is a representation of B in terms of the columns of A. Okay. Turns out that your left inverses, C's, are also projection matrices. Okay. Except they are not orthogonal projection matrices, they are oblique projection matrices. Because if you remember when we talked about representing B in terms of A1 and A2, this is A1, this is A2, this is B. I said you do a projection like this. This is oblique projection. It turns out the left inverses are all possible oblique projections of B onto your columns of A. Okay, and your right inverses simply give you all possible X's that can solve for this. That's because the B's will now give you elements from the null space of A. All right. So that's all I wanted to say about the general stuff about left and right inverses. And it turns out that there are a couple of very special left and right inverses which are called pseudo inverse. Okay. And here I'll again state the conditions: Q and full rank. Okay. If A is tall, okay, the pseudo inverse is usually represented like this: A dagger. It's simply A transpose A inverse A transpose. This is simply one of the possible left inverses. Okay, but it turns out it's a special left inverse. Okay, if it's a fact A, then A dagger is simply A transpose AA transpose inverse. Okay, this also means this is invertible. If A is tall and full rank, A transpose A is always invertible. Okay, if A is fat, A transpose is always invertible, and full rank, it's always invertible. You can verify that the shape of this will be Q cross P. The shape of this will be Q cross P as well. Or sorry, did I do that right or did I mess it up? No, this is correct. Okay. Now, what is so special about them? What is special about them is it turns out this is true. It turns out that the pseudo inverse becomes the inverse when A is square and full rank. Okay, you can verify that. Okay, if A is square and full rank, then you can take the inverse inside, and you can verify that this in fact comes out to be the inverse. Okay, that's one thing that is special about them. What is special about this is, I said the left inverses are projection matrices. Okay, that do all possible oblique projection of a vector B onto the subspace spanned by the columns of A. This is simply the orthogonal projection matrix. This one will give you orthogonal projection of a vector onto the column space of A. Okay. Remember in the last class, to find an orthogonal projection matrix, you need to, what did you have to have? If you wanted an orthogonal projection matrix onto a subspace, what did you need? How did you, yes, how do we find the projection matrix? What did you need to find the projection matrix? Okay, if we needed an orthonormal basis, right? That's where the idea of Gram-Schmidt came about, because we said, well, we want an orthogonal projection matrix. We don't have an orthonormal basis. How do I find an orthonormal basis for this subspace? And Gram-Schmidt procedure gave you one procedure, right? I had mentioned then that It turns out you don't need to do the Gram-Schmidt. This matrix here will do that for you. Okay, not exactly this matrix, but this matrix. We'll come across this later when we talk about least squares. This is simply an orthogonal projection matrix. This is A into A dagger. Okay, that's A dagger. That's a pseudo inverse. A post multiplied by your pseudo inverse. This is your orthogonal projection matrix onto the subspace spanned by the columns of A. That is why that is special. Okay. All right. Now this one. So here, I mean, we can use the right inverse to solve X equals B when we have a system with infinitely many solutions, right? This is special because here, if X equals B has infinitely many solutions, that means if you want one particular solution, you set a criteria and then you choose the best one that satisfies that criteria. If you set the criteria to be, I want a solution to this problem, and I want my X to have the minimum 2 norm. That means the length of the solution has to be the lowest. Okay, if you set a criteria like that, then you can possibly find, say, one solution. Right? It turns out if you use this, if you take A transpose inverse and multiply by B, the X that you get is guaranteed to have the minimum length. Okay, that's what is special about this. Every other right inverse you use to find X equals E will have a length longer than what you get from the right pseudo inverse. Okay. This again we'll come across when we deal with systems with infinitely many solutions. Okay, I will skip one part, but I will tell. But you can do that yourself. Okay. Here, I said A multiplied by A dagger gives you the orthogonal projection matrix onto the column space of A. Okay. That means if I find an orthonormal basis for the column space of A, let's say I call it Q, then Q transpose should be equal to this, right? Because if it doesn't matter what orthonormal basis that you use for a space, if you do Q transpose, it will always give you the same projection matrix. Okay. Now, A is full rank, right? That means I can do Gram-Schmidt. That means I can decompose it like this, right? Simply verify that A dagger gives you Q transpose and verify what is. This is in the slides, but I'd say do it yourself so that you get some practice. Okay. Find out what is A dagger in terms of if A was represented as QR. Okay, that's for the left inverse. You can't do something similar like you did for the left inverse because you can't write A equals QR for a fat A, right? Because the rank is less. There are more columns than the rank. So what you do is you take A transpose. Okay, this is a matrix with full column rank, right? You express that as QR. Okay, and then substitute here, and then find out what you get for. Okay, again, this is in the slides, but do it yourself. Okay, all right. That's most of what I wanted to say about inverses and left inverse and right inverses and pseudo inverses. We'll finish off today with just one last topic for discussion, which is what happens when the matrix is not full rank. Okay, because in all this discussion, I always assumed it's full rank, right? Whether it's square, rectangle, tall or fat, you always assume full rank. This is equals Q. the rank was P or minimum of P or Q. But what if the rank was less than minimum of P comma Q? Then what happens? Okay, if A is square, of course, then you don't have an inverse. If it's A is tall, then also you don't have an inverse. So that means if you have A that is not full rank, there is essentially nothing you can do to get IP or IQ. This you cannot get anymore. Okay, but what you can get, okay, depending on again the shape of A, is if A was tall, you don't get IB or IQ, but you can get something like this. Okay, where R is the rank of the matrix. If A is tall, if A is wide or fat, let me use C because I'm always saying C. Then you can do this. You can still get this. Okay. What about when A is square? When A is square, then both of these can happen. Okay, you can find a matrix C such that if you pre-multiply, you get something like this. If you have a matrix B, which you post-multiply, you get this. I don't remember if you can find the same matrix that will give you this. I'll verify that. I'll let you know next class. Yeah. Okay. So that is the case, right? What happens first when we try to solve a system like this? Okay, let's assume it's tall. Make things a little easier. It's tall, but it's not full rank. Can we solve it? When can we solve it? Well, as always, B has to be in the span of A. If it's not in the column space, of course we cannot. We can solve it if B or the column space of A, right? But is the solution unique though? Turns out it's not, because even though B is in the column space of A, because you have more columns than the rank R is less than. So R is less than Q. That means you have too many columns. It means if B is in the column space of A, then you get infinitely many solutions. If B is not in the column space of A, of course you cannot solve it. Okay. What you can find is a projection of B onto the column space of A. Okay, but then again there are infinitely many solutions that will give you the same projection. Yeah, when you don't have full rank, you forget about getting a unique solution. There are no unique solutions anymore. If at all the system can be solved, you always have infinitely many solutions. Okay, alright, that's all I wanted to discuss about this module. I know there is a lot, but again, if you go back and then look at it slowly, most of it should make sense. If it does not, let me know, and then we can discuss about things that are still not clear. Okay. Are there any questions so far? We have 5 more minutes. No, this I will this I need to think about. I'll verify and let you know. If A is square and not full rank, my hunch is you might be able to find the same matrix that gives you this. Not full I. You might be able to find the same matrix that satisfies this, but I'll verify.